дня всім. Перепрошую, що сьогодні онлайн. Отже, тема моєї
Прошу.
доповіді така, як і вчора, про дослідження складних комплексних систем за допомогою квантового програмування, а також можливі застосування тих результатів досліджень, а також інших квантових, відомих квантових алгоритмів за допомогою з використанням для розв'язання задач біології, біофізики. Отже, я зараз поділюся екраном.
Прошу. Прошу.
Ви вже бачите, так? Супер. Отже, квантові технології це не майбутнє, це
Не
теперішнє.
чути?
Чути мене добре?
А.
Бо я
Вас чути добре, але поступила пропозиція, якщо можна англійською мовою зробити доповідь. Як ви на це дивитеся?
добре, супер.
От,
Добре.
прошу. Дякую.
Okay. So the title of my presentation is the same as I presented yesterday, but today I have possibility to present more detailed results and the detailed plans for future studies. And so let us consider what does it mean that we have quantum programming, and what about quantum technologies and their possibilities today. So quantum computer is a powerful tool, powerful device that operates on the basis of quantum mechanical principles. What does it mean? We operate on quantum bits, on the states of quantum bits, and we change the states due to action of different quantum gates. And in quantum world, we have superposition of quantum states. So we have possibility to have in our quantum state different terms and operate with all these terms simultaneously. Also, in quantum world, we have quantum entanglement, which is fascinating property and the important resource of quantum programming. This is because due to this some kind of correlation between different quantum states of quantum bits, we can we can act on the state of one qubit, and due to this action, due to entanglement, the state of another qubit will be also changed. Also, quantum measurement is very important because the nature of quantum measurement is the following, that we cannot, in general case, we cannot predict the result of measurement, the result of quantum measurement. Therefore, doing quantum calculations, we have to consider numbers of shots and to obtain some statistic of results. So on this picture, on this slide, you can see the quantum device, IBM's quantum device, and you can see also quantum device which was designed for studies for students, SpinQ, 3-qubit quantum device. It was in University of Oslo. So what about difference between classical bits and quantum bits? I told in previous slide about superposition of quantum states, and in this slide you can see this property. So in the classical case, if I have one classical bit, I can obtain just two values, 0 or 1. In quantum case, if I have quantum bit, I have superposition of zeros and ones, and this superposition is written here in this slide. This superposition contains also constants, and I can write the information, even information I use in biophysics, on these states 0 and 1s, but also I can write this information, I can contain this information in these constants which are complex. So I have various possibilities to solve different problems, even if I have just one qubit. So I can write my classical information on this is known as basic encoding on this basis states, 0 and 1, but I also can contain my information on in this constants, C1 and C2. And very important that in quantum case, I can prepare just for one qubit, I can prepare infinite number of quantum states because I can choose different constants. Of course, the normalization condition has to be satisfied, but even in this case, even with taking into account this condition, I have two parameters which can be changed, and I can prepare arbitrary state. So this is important difference. Even if I have just one qubit, if I have two qubits, I have four possibilities that two qubits can be in the state, for instance, 0, 0, then 0, 1, 1, 0, and 1, 1. So four possibilities for two qubits. Therefore, in my superposition of quantum state, in the general case of superposition, I have four basis vectors and I have four constants which are also complex. So I can write my information, my classical information, in each term and in each constant. In the case of n-qubit superposition state, I have to say that today we have 1,121 qubit device, IBM's quantum device. So in the case of this number of qubits, I have two to this number, to 1,000 quantum states that are in my superposition, in superposition of n-qubit state. And I operate with each term simultaneously. So I do my work in parallel. This is known as quantum parallelism, and this is, I have to say, that the most important resource of quantum supremacy. Quantum supremacy means that I can solve different problems, different classical quantum problems with quantum device faster than in the classical case. What about operations that I can perform in my quantum device? Some of them, part of them, is very similar to the classical. For instance, it is not operator or controlled not operator. This is classical if. So I can act with not gate on a qubit. In the slide, you can see what does it mean. What is the quantum protocol in this case? So I act with not gate on qubit 0, and I achieve the following results. So if my state is 0, I obtain 1, and opposite result in another case. Controlled NOT gate is 2-qubit gate, so I act with this controlled NOT gate on 2 qubits. So you can see here in the slide qubit 0, qubit 1. And this small point corresponds to the qubit, describes the qubit which is controlled. So if the state of qubit 0 is 1, the operator, the NOT gate, act on the state of qubit 1. So you can see these examples. This is simple way of introduction, this controlled NOT gate. So if the state of qubit 0, is 1, the state of second qubit is changed. And the same in this case. And if the state of qubit 0 is 0, we have the same result. So controlled NOT gate acts as one operator. So we obtain the same state. Also, I have to note very important gate in quantum case, which is Hadamard gate. And we cannot realize this gate in classical computer, in a classical device. This is because this gate acts on qubit and creates the superposition. superposition of states 0 and 1s. So this is very important. There are numbers of gates in quantum devices, and we can realize them, but these 3 gates are presented just for example, just for knowing and understanding what will be presented on the other slides of my presentation. So quantum protocol have, for example, the following structure. So if we have 3 qubits, the initial state of these qubits at the beginning of my quantum programming is 0, 0, 0. Then I act with different gates here. So you can see Adamar gates and 2-qubit gates, RZZ gates. These are gates corresponding to operator of evolution of spin system with Eisen model. So we have interaction ZZ and so on. So acting with these gates on the state of qubits, we prepare some state at the end of quantum program. But in the contrast to the classical programming, we have also to make the following step of, we have to perform the quantum measurement, because we have to find this information from quantum world. And this measurement here in this quantum protocol, where we have measurement in standard basis, so we find projection of states of each qubit to z-axis, and we write this information from the quantum measurement on classical bits. So this C is classical, correspond to the classical bits. Of course, if I have multi-qubit quantum program, it is not convenient to use such presentation of this program. So to write for each qubit these lines and put these gates here. So we use Python, we use Qiskit in the frame of Python, and we write this program in this way. So what about the results of studies, the results of my studies? And what about studies of complex systems with quantum programming? In my recent papers, I focused on the studies of graphs and also other complex systems with quantum programming. So how can we study such a classical objects with quantum devices? The idea is the following. So we can study whatever we want, whatever object we want. It can be classical object, quantum object, but we have to find very clear mapping of this classical object to the quantum one. So if we have such a mapping, we can study properties of classical objects, quantum objects with the help of quantum programming. In the case of quantum states, in the case of classical graphs and quantum states, we can map each other in the following way. So in graphs or in complex systems, we have numbers of different nodes, and they are connected with each other with links. And to describe such a structure, for each node, we consider the following representation, that each node is represented with the qubit. And the links between nodes are represented with action of 2-qubit gate. So 2-qubit gate, for instance, it can be this one. So this gate acts on the state of 2 qubits simultaneously. Or this one, it can be whatever you wish. But the structure is the following. So I have to consider the product of these 2-qubit gates. We have these 2 indexes, so this operator acts on the qubit I and qubit J. I have the initial state. The initial state of n qubits And the number of qubits corresponds to the number of nodes in my graph. So if I have such a mapping, such clear mapping, I can say that I have quantum graph state. Of course, you can find another ways of representation of this classical object, this graph with quantum properties. But this representation have achieved many attention recently. So I have to say that, for instance, in this paper, the authors considered graph states constructed with controlled Z operators, and they found that the quantum device can be IBM's quantum device can be prepared, we can achieve the state which is entailment state, graph state corresponding to the chain. Also, in our paper with Natalia Susulovska is my PhD student, we considered a more general case of these states, these quantum graph states. So we considered controlled phase gates instead of controlled Z gates. And we also studied the entailment, and we obtained that very interesting result can be obtained due to the relation of the entailment to the classical property, which is degree of vertex in a graph. So we have entailment E, and this expression contains all these parameters we have in our quantum state, but also we have this parameter n, which is indexed L, and this parameter is degree of vertex in a graph. So we have a relation of quantum properties with classical ones. Just to show the results of quantum programming obtained in this year, so it was 5 years ago, on a 5-qubit quantum device, and these crosses correspond to the results of quantum measurement, results of quantum calculations on real quantum device. And this line is theoretical result. So we have some kind of good agreement of results of quantum calculations with classical. What about general idea of my studies of the entailment, my studies with my colleagues, with my students, and general results? So why do we need to study this entailment? This is because entailment is an important resource of quantum programming, and knowing entailment is important in order to improve the quantum protocols, to improve the quantum programs. So we studied entailment of various multi-qubit quantum states, and we also considered quantum graph states, and we have the relation of entailment, relationship between entailment and the degree of the vertex or node in the graph. Also, recently, not very recently, so 2 years ago, I considered another case of quantum graph state, and it was RXX gates and various parameters here, and this state corresponds to the graph, which is directed and weighted graph. So each link is described with some parameter and the direction, and the results of quantum calculations, the difference between the quantum calculations and the results of classical studies, you can see in this presentation. And what about another studies? Another problem is to find some algorithms, to present the idea how to calculate some parameters of classical objects faster, so maybe easier way than in classical case. So how can we achieve this result? We also have to find some relation between quantum properties and classical properties. Very interesting result can be obtained if we consider, for instance, the quantum states, evolutionary quantum states of spin systems, It can be various spin systems, but at the beginning, in quantum programming, we consider Eisen model. Why do we consider this model? Because we can realize the operator of evolution in a very simple way on a quantum protocol. Because all operators commute and we can achieve this sum, we can represent this the sum of terms in exponent with the help of products of exponents. So we considered this case and obtained that the mean values of Hamiltonian in different powers, for instance, Hamiltonian squared, Hamiltonian to the third power, Hamiltonian to this fourth power, is related with the number and characteristics of closed cycles in graph. Or in other words, it can be triangles, squares in graph, and their parameters. To find the number of triangles or to find the weights in a triangle in a graph, it's not easy in the classical case, because for each vertex we have to check, do we have triangle or not? What is the parameter corresponding to the links between this vertex with another? So it is, if we have complex system and we have numbers of nodes, it's not so easy. But we have showed that on a quantum device, we can solve this problem just considering and just calculating the mean values of Hamiltonian. And to do this, we considered the operator of evolution and we calculate this on a quantum device. So you can see these dots correspond to results of real quantum programming, and this line corresponds to the results of theoretical studies. So the quantum algorithms have to study these properties have been proposed, and we hope that this algorithm opens the possibility to achieve this quantum supremacy in studies of such a property, such graphs. Why do we need such characteristics of graphs? This is because the number of triangles, the number of squares is related to the stability of graph. So this is important parameter in graph theory. Also, we considered more complicated problems. So we considered bipartite graphs. So graphs that can be explained as we have two types of nodes, and we have links between just nodes of different types. So, like in this case. And we propose the following states describing this graph and calculated the entailment and also other parameters, other properties. So if you are interested in details, in each slide I put the papers where the results are presented and published. So we studied the entailment distance and we considered such a protocol. So we have gates corresponding to the initial state and to the graph state, and we measure the mean value of spin operator here and obtain the result. So the results of measurements are presented here. We also have relation with the entailment with the degree of the vertex. Also, with the help of studies of quantum correlators, we can find such a property like a number of vertices with odd and even degrees in my bipartite graph. Also, I considered tripartite graph. So the state corresponding to such a graph is the following: the entailment was found. What about importance of these results, and can we use these results in biophysics, for instance? Yes, we can, because graphs with the help of graphs, we can describe different systems. Even in biophysics, we have protein-protein interaction networks and other interactions in biophysics. But also these results are important from the fundamental point of view because the graphs, multi-qubit quantum states, quantum graph states are used in various quantum algorithms, and they are quantum error correction algorithms, preparation of different states and tangent states, and also quantum machine learning, and so on and so on. In literature, there are various quantum algorithms already developed, but of course, not all of them are used in practical cases. So they are developed, and we are looking forward of improving of quantum technologies and achieving of quantum supremacy, which is predicted in all of these algorithms. So they are, for instance, optimization problems, factorization, study of classical quantum system, and so on, quantum machine learning. And these various algorithms can be used also in biophysics. First of all, I have to mention the following. That we can calculate the energy levels, also we can calculate eigenstates of different quantum systems, also the quantum systems which are considered in biophysics with the help of quantum programming. So there are different algorithms developed for such studies. I, with my colleagues, we also developed an algorithm how to find the energy levels of different spin systems with different interactions. Also, we can simulate different interactions. We can simulate open quantum systems with the help of quantum programming. We can consider optimization algorithms, so we can find the minimal value or optimized value of some problem. Why do we consider such an algorithms? Why such algorithms have been developed? This is because quantum superposition. So in the case of quantum programming, we can consider different possibilities simultaneously. So for each term in superposition, we have such a mapping of each term in superposition to some possibility, and we can check simultaneously different possibilities due to superposition, due to quantum probabilities, and find the solution. And also quantum machine learning algorithms. So I also did, and I will do some studies in the frame of quantum machine learning. So in quantum machine learning, we consider the same problems as in classical machine learning, but with the help of quantum device. And it is very important quantum machine learning to have multi-qubit quantum state described with different parameters. For instance, this state is presented in this slide, so we have different parameters in this state. And first of all, we have to know the entanglement because it is a resource of quantum programming. So thank you for your attention. I also prepared just a small program to show how it works in quantum computing. But maybe you have some questions, and I will prepare this very small part of my presentation to the end of this lecture.
Thank you, Khrystyna. Thank you very much. Very nice talk. And sure, we have some questions. Please, I invite you to.
Yes, sure.
Sergey, please.
Khrystyna, thank you very much for a very interesting lecture. This is completely new for our field of research, probably for me. Somebody maybe already knows more. But as for me, I would like to understand how we can check quantum supremacy. And if we can use, for instance, some problems that we can solve for some biological molecules to check quantum supremacy.
Thank you for the question. So have we achieved the quantum supremacy, and have we obtained the number? What is supremacy? So, for instance, Google, maybe 5 years ago, published a paper. Scientists from Google published a paper that they solved some problem faster, in million times faster on a classic quantum program with a quantum computer, and this program cannot be solved with classical computer. So we have to calculate the complexity of the quantum algorithm, and compare these parameters, and then run the quantum program on a quantum device and achieve this quantum supremacy. So to calculate this, we have to calculate the time which is needed to run your program on a quantum device and a classical device, and compare them and obtain the result. Do we have the quantum supremacy or not? So for problems in biophysics, in order to show this quantum supremacy, yes, of course, we can consider such complex systems, but the technologies, the quantum technologies which are known today, which are developed today, so we have no possibility to achieve right now. So we have to develop maybe new algorithms to achieve quantum supremacy now with the help of quantum devices, which are noisy quantum devices. So this
Thank
is...
you very much.
Thank you, Khrystyna. So quantum supremacy, and we expect that our that quantum computers will be more will provide us higher performance than classical computers. But what about accuracy, computational errors, and so on? Is there some problem when we do calculations?
Yes, sure, we have problems. So if you run small protocol, we have a good agreement of theoretical results and quantum results. But if you run a multi-qubit quantum protocol, because of gate errors, because of the errors of measurement, which are of the order, the 1 qubit gate errors are of the order 10 to minus 3. 2 qubit gate errors are of the order 10 to minus 2, and each measurement has characteristics which describe the errors of measurement. So we have to calculate and find.
There is a problem with double precision.
Yeah, there is a problem. Yes, of course, there is a problem. But if I have just 1 minute, I would like to share with you, because I am online, so I can share the quantum program, the example quantum program. I can do it with the help of IBM's quantum devices, well, IBM's classical simulators of quantum devices. So I consider Python, and I import Qiskit, which with the help of Qiskit I can use different devices which are developed. And I create quantum protocols, for instance, this NOT gate, and I can have different ways of describing of my quantum states, for instance, with the help of Bloch sphere. And so 1 qubit quantum protocol, 2 qubit quantum protocols with controlled NOT gates, and so on, and Q sphere for this quantum state. And then the result of measurement is the following. So what do I have? Results of quantum programming. So I have to consider numbers of shots. This number 10 was just considered, for example, for students, but traditionally I consider 1,000 of shots, and then I obtain statistic. For instance, this for 1 qubit case, I have statistic how many times I obtained the state 0 and state 1. For instance, in the case of 10 shots, I obtained 4 times state 0 and 6 times state 1. So this result is the result of quantum programming, and on the basis of this histogram, I can find the solution of the problem in general case. Of course, there are algorithms that can be, so we can use just one shot to solve the problem with some types of algorithms. For instance, this Deutsch-Josse algorithm, Bernstein-Mazerani algorithm, and others.
Okay, thank you, Khrystyna. I don't see, maybe somebody, is there somebody who wants to ask a question? No? Yes, Nazarit Kash, please.
Good day, everyone. First of all, thank you for your presentation. I just want to ask one question about limitation of implementing biophysics into quantum computing. Is there any limitation of the size of the molecule that we can just compute something in practical way?
The limitation is in number of qubits needed to describe this molecule on a quantum device. So the number of qubits which are achieved nowadays is 1,121 qubit for IBM quantum device. And the number of qubits also depend on the properties you would like to study for this molecule on a quantum device, because very often you need ancilla qubits to realize a quantum protocol. So there are various limitations.
So now it's the limit that we just can explore some small molecules just for around not less than 10 atoms, yeah? As I understand.
Yes, but of course, if we have 1,000 IBM's 1,000 qubit IBM's quantum device, because of quantum errors, we cannot use all qubits simultaneously. So the limitations are also in the quantum errors, which are nowadays, it's very important problem to solve this. So to achieve error correction.
Okay, thank you.
Thank you.